Sometimes people will say that mathematics is a kind of language that you use to communicate the quantity to other people. Let's say if you want to tell other people how many apples you have, then you can just tell them a number and that will communicate how much or how many apples you have. If you want to communicate a game to other people, so let's say if you have a game and you want to describe that to other people, well, in game theory, there are two ways to do that. One way is to use a tree, and that is called a game in extensive form, and that's going to be what we're going to talk about in this lecture. Another way that we can use to communicate a game is to use a matrix, and we're going to talk about that in the lecture 5. So for now, let's talk about how can we write a game as a tree. Now, I can talk about the terminology first, but this will sound a little confusing. So at first, let me talk about this example here. So let's say I have a game, and this game, there is Alice and Bob. So Alice is going to choose head or tail, and then Bob will see what Alice chooses, and then Bob himself is going to choose head or tail, and then Alice will pay Bob $1 if their choice is the same, and then otherwise, Bob will pay Alice $3. Now, to write a game as a tree, we will normally start with a node. So if you had never had graph theory before, then don't worry too much. Basically, what we have here is a circle which will represent the game state, the state of the game. And then underneath this game state, we will have the possible actions. So these are the actions that the players can take. So because the first thing that happens is that Alice will choose head or tail. So that means at the first state, we will have Alice. So here, Alice is the player. Or sometimes we will say that the Alice has the move. Sometimes we will also say that Alice has the move. Alice has the move. And then we say that Alice can choose between head or tail. So Alice will have two possible actions here. So one action is to choose head, and then the other is to choose tail. Notice how there's nothing above the first, so Alice is the first player here, so there's nothing above it, and we will say that this is the beginning of the game, or sometimes we will call this a root node as well. So it's basically the first node is the starting node of the game. So then, once Alice shoots head or tail, Bob is going to play. If Alice shoots head, then Bob is going to play, and if Alice shoots tail, then Bob is going to play. And Bob's option is the same in both cases. So once Bob comes into play, Bob can choose either head or tail, and then head or tail. And then that's the end of the game. So in a nutshell, this is what happened then. So the first node that you see up top here, this is the start of the game, and letter A, this just means Alice is the player, and letter B here, this just means Bob is the player. Bob is the player, or Bob has the move. And then, so Alice can choose between two actions, head or tail. If Alice chooses head, then Bob has two possible actions. Bob can choose head or choose tail. And that's the same here. If Alice chooses tail, then Bob can choose either head or tail. Now, once Bob chooses, then this is the end of the game, and we will call this node the terminal node. At this terminal node, it's going to be the end of the game, and we see earlier that at the end of the game, Alice is going to pay Bob $1 if their choice match. Otherwise, Bob will pay Alice $3. So to represent this payment, we will usually write that as a vector. So we will have a vector. So let me kind of write that here. So because we have two players, so I'm going to have two numbers here. The first number that we will see, this is Alice payoff. So this is Alice payoff. And then the second number is going to be Bob's payoff. Now let's see. We say that Alice will pay Bob if their choice match. So now in the first possible ending here, Alice chooses head and Bob chooses head. So because their choice match, So this is the first case when Alice is going to pay Bob. So that means Alice lose $1 and Bob get $1. So what this means is that in this option, Alice is going to lose $1 and Bob is going to get $1. Now in the second possible ending here, Alice choose head and Bob choose tail. So their choice doesn't match. So Bob will pay Alice $3. So what that means is Alice will gain $3 and Bob is going to lose $3. And that's the same thing here. If Alice play tail and then Bob choose head, then Bob will pay Alice $3. So Alice has $3, Bob lose $3. So this is the purple scenario. And then for the last one, this is when Alice choose tail and Bob choose tail, so their choice match. So Alice is gonna pay Bob $1. So that means Alice will lose $1 and then Bob will get $1. Let's now take a look at the part B here. This is actually the same game as the part A, but the difference here is that Bob will not know what Alice choose. So you can kind of see that the first game Bob kind of cheat a little bit because he can kind of see what Alice does. So then basically, if I am Bob and I see that Alice play head, then I can just choose the same thing so that I get money from Alice. So Bob is kind of cheating a little bit here. So part B fixed that. So now Bob is not going to see Alice's choice. So that is the only difference. So how should we write this game then? So it kind of play out the same. Alice choose first between head or tail, and then Bob comes to play next, and then Bob choose between head or tail, and then choose between head or tail, and then the ending is all the same. It's going to be -1 and 1, and then 3 and -3, and then 3 and -3, and then -1 and 1 here. So, well, so far this is the same game as what we have up above. So how should I represent the fact that Bob is not going to know what Alice does? Well, the way we can do that is we are going to just draw a circle, or in this case it's gonna be like an ellipse around the Bob's node here. So when I draw this circle, or well, basically the ellipse here, it means that when Bob comes into play, he will not know exactly which node in this orange circle that he is at. So when Bob comes into play, he's not gonna know for sure whether he's at the left node or he's at the right node. He knew that he's somewhere within this orange circle here, but he will not be sure where exactly he is. So this is how I can represent the fact that the Bob has some restriction on the information structure of the game. Now then, for the third part, the only difference here is that Alice is actually going to toss a coin instead of choosing it herself. So, the difference here is that we cannot draw the game as what we used to anymore, because when we do it in the previous two parts, we have this node up first where Alice play the game and Alice choose between head or tail. So when I do this, this means Alice is the player. But for part C, well, Alice tossed a coin, so even though she is the player, but she's actually not really deciding head or tail by herself. It's kind of more like she tossed a coin, so she let the chance decide whether or not it's going to be head or tail. So when that happens, what's going to happen is, instead of saying that Alice is the player, I'm going to say that Chance is the player. And that kind of makes sense because, well, the difference between Chance and Alice is that if I said Alice is playing, that means she has to make the decision whether or not it's going to be head or tail. But when she tosses a coin, that means she is not making the decision herself. She let it to be decided by Chance. So in this case, I'm going to say it's a Chance node, or sometimes we will say it's the player 0. I'm just going to put number 0 here. Or sometimes I'll say it's just a God node. So it's God who decides how to, which part he's going to take from here, whether it's going to be head or tail. Or sometimes if you play a video game, you probably have heard of the RNG, or random number generator God, something like that. Or maybe just an RNG, just a random play. So here, because Alice chooses a coin, so then that means there is two possibilities here, head or tail, same thing. But there are probabilities that come equipped with this part now because, well, this is a chance node. So the probability of getting head or tail, this is going to be 0.5 and 0.5. So this is the difference between part C and part B here. Let me actually color this green, just so we notice the difference. So then, well, the game play out the same next. So we have Bob comes into play. And then Bob will not know the outcome of the toss, so I'm gonna draw a circle here. So Bob doesn't know whether or not, whether the god choose head or tail for Alice, and then he will have to make a decision anyway, whether or not it is a head or tail, and then head or tail, and then there are 4 possible outcomes, and the outcome is the same thing. So it's gonna be, let's see, -1 and 1, 3 and -3, 3 and -3. And then -1 and 1. Okay, so now let me actually go back and talk about some of the terminology that we see earlier. So we say that a game is in extensive form if it is a tree. So what you see in this example here is this is the game in extensive form, which is written as a tree. And then each node, so each node that you see here, this is the circle thingy. So this is the technical term for that is the node or the vertex. It represents the state of the game, so it represents how the game has progressed so far. So the root node is going to be the node that we see up top. So that's going to be the start of the game. It's the first node that the game has. So then we see earlier that the node will have a player's name attached to it. So in a mathematical terms, we can say that each node, the nodes can be partitioned into different sets where the label of each node is basically the player who has the move of the player who is going to play at that state of the game. And sometimes we will also have this chance set or the chance node. It's kind of what we see in part C here. And then all the rest are the player's set. Now, the edge that comes from each node represents the player's choice when the game is at that state. So we're gonna see earlier that when at the start of the game here, because this is a list node, so a list has 2 possible choices, and then for each of the node down here, Bob is the player and Bob has 2 possible choices. So the edge that comes from each state of the game represents the action that the players can take. And then the set can be partitioned into information set. So again, information set is the kind of tools that help us represent how the player, how the player doesn't know the state of the game that he is in. So there is some information structure, there is some secrets about the game when there are information set, the orange thingy here. Now, there is one details about information set. So the moves that come from each node in an information set is going to have to be the same. For example, let's see if I have a game that looks like this. And then this 2 node is in an information set. So let's say if the left one has 2 possible actions, then the right one need to have 2 possible actions as well. So if the left one has 3, for example, the right one would also have 3 possible actions. And this is because, let's say if the left one has 3 and the right one has 2, then when this guy, let's say this is for Bob, when Bob comes into play, then he can assess how many actions he has, and then he can be able to tell which node he is at. So for example, if he look at the board and he see that, oh, there is 3 possible things that he can do, then he will know that he is at the left node. But if he look at the board and he see that, oh, there is 2 possible things that he can do, then that means he's at the right one. So if the number is not the same, then the player will be able to look at that and tell which one he is at. So this is no longer a secret to Bob. So if the left one has 3, the right one will also have 3. So this is what we have here. And then for each terminal node, so the terminal node, we talked about that earlier. This is the bottom node, so that represents the end of the game. At the end of the game, there will be a payoff vector, and that represents how much money or how much utility each player gets. We're going to talk about utility later. And the number of the terminal node, this is going to be the number of ways that the game can be played. For example, in the first example earlier, notice how there are 4 bottom nodes, there are 4 terminal nodes, so there are 4 ways that this game can be played. Alice can choose either between head or tail, and then Bob can choose between head or tail, so there are 4 possible ways that this game can be played. And we say that a game is of perfect information, so this means there is no secret in this game. Everyone knows everything if all information set are singleton. So it's kind of what we have in the first scenario here. Everyone knows everything. There is no orange bubble. But you can see how for part B and part C there are orange bubble. There are some secrets in the game. So these are not the game of perfect information. Now, before I end this lecture, let me also talk about some pros and cons of representing games by the using a tree structure like this. So the pro is that it is easy to understand. You can kind of track the state of the game by just following the tree nodes here. However, the con is that the game can be quite big. For example, if I want to draw the game tree of chess, notice how, well, let's say for the first player, there are 20 possible options. So if I were to draw a tree for this, that's going to be like 20 nodes already. And then the opponent has like 20 possible options. So each of the possibility here will have its own 20 descendants. So from the first 2 turns, there's already like 400 nodes that we have here. So if we keep drawing a game tree like this, we'll have like billions of nodes. So the game can get pretty big pretty fast. And it can also only handle games that are discrete. For example, if a game involves, let's say like a player choosing numbers in the interval 0 and 1. So I cannot draw a game tree of this because I can only have like a finite number of edge for each node here.